Okay, cool. Let me share my screen. Am I fine to start now?
It's okay to start now. We have
Great.
Isaac Martin, who will talk about algebraic de Ram cohomology and the Hodge spectral sequence.
Yeah, that's the plan at least. All right. Hello everyone. Thanks for turning up to this talk. Let me get the right screen set up. One sec. There we go. Cool. All right. Yeah. Hello everyone. I'm Isaac Martin. Yeah, and today I'll be talking about the algebraic de Ram cohomology and the degeneration of the Hodge spectral sequence. Just in advance, I realized yesterday two things when I was practicing this presentation with a rather disinterested friend. I realized that this is a fairly dry topic, I apologize in advance for that. And also, I have it's very different writing about this versus speaking about it. It's hard to say a lot of these words succinctly. So just I'll try and keep that in mind, but here we go. So before I jump right in, I'd just like to oh, sorry, I need to switch to presentation mode. Single page, cool. Does that work? Okay, there we go, cool. So yeah, before I jump in, just into the land of technicality and abstraction, I'd just like to talk a little bit about classical algebraic geometry. So classically, in algebraic geometry, we study things called algebraic sets, and these are just the vanishing sets of polynomials. Here, this is just an elliptic curve. We care a lot about these in number theory. They're famous because the proof of Fermat's theorem, and it's an example of an algebraic set. Perhaps more exotically, this is something called the Cayley surface. It's an algebraic set. It's the vanishing set of this polynomial, and we care about it because it's something called a degree 3 nodal surface. Now, I don't know much about the Cayley surface in particular, but one thing the reason I want to include this is it makes it, at least to me, it's more obvious looking at this picture that that algebraic sets come equipped with a lot of topological data. And in fact, one might argue that one of the main purposes of algebraic geometry is to try and access this topological data via algebraic methods. And so one of the best ways we do that is through cohomology. So this talk is largely about trying to develop a cohomology theory for varieties. And as is the case for many things in algebraic geometry, we take inspiration. One route we might take in trying to do this is by taking inspiration from differential geometry. In differential geometry, we have this very nice de Ram isomorphism, which tells us that, at least for real smooth manifolds, we have an isomorphism between singular cohomology and de Ram cohomology. And now I like to think from a higher level perspective, I'd like to think of singular cohomology as something that's sort of topological-ish, and de Ram cohomology is something that feels more analytical. So that's nice. And then there's something called Serre's Gaga principle, which tells us that algebraic geometry is very closely related to analytic geometry. And so if we're trying to create a cohomology theory that works for algebraic varieties, one avenue we might take is by attempting to first use some adapted form of de Ram's isomorphism to move from topological stuff to analytic-ish stuff, and then use something like Serre's Gaga principle to move from analytic stuff to algebraic stuff. And now that's great. And if you try and do this, however, you immediately run into a rather big problem. Just if we leave varieties for a second and instead talk about complex manifolds, which are a lot closer, at least in spirit, to real smooth manifolds, you realize that this isomorphism just can't hold. It fails pretty badly for complex manifolds. And so if we want to follow something like this strategy, hope is not lost, but we have to seriously adapt what de Ram cohomology is. And so the way we go about fixing this is with this strategy. So the first thing we're going to do is we're going to try and adapt the de Ram complex to work with varieties. That's relatively straightforward. It just requires a bit of commutative algebra and some chapter 2 hartshorn topics. And then once we do that, we're going to realize that instead of the cohomology of this complex, we want to consider the hypercohomology of this complex. And that's turns out to be what fixes our problem. And we call this the algebraic de Ram cohomology of a variety X. So, but however, once we do that, hypercohomology is infamously terrible and horrible to compute. So we need to find some way to work with it. And the way we do that is by forming a spectral sequence to somehow relate a nicer cohomology, Hodge cohomology, to this new algebraic de Ram cohomology. And then once we've done that, finally, we use something like Sayers-Gaga principle, or in this case, just some very cool characteristic P techniques to prove that these two cohomology theories are the same, that Hodge and de Ram cohomology give us the same thing. And this is pretty cool. However, just for time constraints, I realized I can't really talk about this, which is also somewhat fortunate because this is the step that I understand the worst right now. But hopefully we can still get something out of these first few constructions. Yeah. So to see sort of why this is kind of strange and why this is a very cool result, might consider this. So Hodge cohomology is normally defined like this. This is just normal sheaf cohomology right here, and it's a direct sum of sheaf cohomologies. But we can also realize Hodge cohomology as the hypercohomology of this complex right here. Now this looks a lot like a de Ram complex, but you'll notice that we have very stupid maps all along here. Our chain maps are all just the zero maps, and it turns out this gives you Hodge cohomology. And so this theorem on the previous page is actually just asserting that these two hypercohomologies are actually identical, which is very surprising and very non-obvious, at least to me. This is the normal de Ram complex right here with the exterior, some analog of the exterior derivative, and this is that same complex but with all of the chain maps replaced with zero. But it turns out that this does work with nice enough assumptions. So moving on, our first goal was to adapt differentials to work with varieties. And so in commutative algebra and algebraic geometry, the correct notion is that of Kähler differentials. Here we're just going to define Kähler differentials for commutative rings because they're just easier for me to visualize at least, and then we're just going to claim they globalize the schemes. So a Kähler differential is just is just this. So if we take B to be some A algebra, A is a commutative ring. If we take B to be an A algebra, that just means we have a ring homomorphism from A to B. And if we take M to be a B module, then an A derivation on B is just some A module homomorphism D, which additionally satisfies the Leibniz rule. And so that's what derivation is. That's fine. And then we can, once we know what derivations are, we can form the module of Kähler differentials like this. We can take this map from B tensor B to itself, defined right here, and the module of Kähler differentials is what we're going to is just this. It's the quotient of the kernel of this map with itself squared. That's fine, but one would hope that if we're calling something the module of Kähler differentials, that it satisfies some universal property. Like on the previous page, our definition of a derivation depended on our choice of a B module M. So we'd hope that the module of Kähler differential satisfies some universal property, and indeed it does. It turns out the module of Kähler differentials comes equipped with the map. It's just called the universal derivation, and it's defined like this. And it has a nice property that if we take any other derivation from any derivation D prime, then we can realize D prime as a composition of our universal derivation with some unique B module homomorphism from the Kähler differentials to M. And in fact, this definition, if we can alternatively define the Kähler differentials to just be any B module that satisfies this universal property, any B module that comes equipped with a map that satisfies this. However, we prefer this definition here because this is the one that globalizes immediately to schemes. Great. So once we have the Kähler differentials, just as we do in differential geometry, we form differentials of higher degree by just taking wedge products of the Kähler differentials with itself. And once we do that, we find that there's a nice family of maps that form some analog of the exterior derivative and satisfy the nice the chain map property, I guess. And we obtain a complex that looks a lot like the de Ram complex, and in that vein, we call it the algebraic de Ram complex of X, and we denote it like this. Cool. So that's the first step. We've adapted the de Ram complex to work with varieties, and now we need to talk about we need to figure out a better definition of de Ram cohomology. Now, as I said, the correct thing here is to consider the hypercohomology of the sequence. Now, by analogy, hypercohomology is to a complex of sheaves as normal cohomology is to a single sheaf. For those who are interested, here's a better definition right here. But if I'm honest, it's not very important to this talk to know what hypercohomology is exactly, and I personally treat it mostly as a black box. But what we do care about is that hypercohomology satisfies these two very nice properties right here. So this first property is that if we have any quasi-isomorphism of complexes, then any quasi-isomorphism induces an isomorphism on the hypercohomology of those complexes. And now, a quasi-isomorphism is just a map of complexes that that induces an isomorphism on the level of homology. So this property just says this behaves similar enough to normal cohomology. And then the second property that we care about is that if we take a complex, if F is a sheaf and we take a complex called the complex concentrated in degree 0, that's just going to be this complex here where we have 0 maps everywhere and we have F in the 0 degree position. If we take the hypercohomology of this, then this is just the normal sheaf cohomology. And so we get back just normal sheaf cohomology. These are the two properties that allow us to do anything with hypercohomology at all. This is what's going to be important to us.
Isaac, are you on a new slide? It hasn't changed for me. It's still on the algebraic de Ram complex.
Is it moving? Oh, no. Crap. It isn't? Oh, I'm sorry. That's bizarre. Let me try resharing. Yeah, I'm on a new slide. I'm sorry. There we go. Yeah, very sorry. Hopefully that, can you see it now?
Yes, thank you.
Cool. Yeah. So the main essential part of this slide is just these two properties. So that I was talking about. That if we take the hypercohomology of a sequence, it satisfies these two things. So if we have a quasi-isomorphism of complexes, then the hypercohomology of those complexes is the same. That's property 1. And then the second property is that if we take, if F is a sheaf and we take the complex concentrated in degree 0, that's just this complex right here. So we have zeros everywhere except for this degree 0 term, which is F. We want the hypercohomology of that to just be the normal sheaf cohomology. Yeah, and so and these are the two properties that are important to us, and it's what lets us compute hypercohomology at all, at least in this context. And so to have that, we're going to define the algebraic de Ram cohomology of a variety to just be the hypercohomology of the de Ram complex that we defined on the past slide. Great. So why is this the correct definition? Well, just at a bare minimum, one would hope that that singular cohomology and de Ram cohomology are isomorphic for, say, a complex variety. And that's not true if we were to just take the cohomology of the de Ram complex, but it is true for hypercohomology. So to see that, just if we take some sheaf F naught and we take a resolution of that sheaf right here, it's easy to see that taking a resolution like this is the same, or it gives us a quasi-isomorphism between the complexes, between these two complexes. So here, this is just the complex concentrated in degree 0 that I talked about before, and this is the complex obtained by just deleting this first F naught in this resolution up here. So we get a quasi-isomorphism between this because their cohomology groups are the same. And now by the properties on the previous page, because this is a quasi-isomorphism, that tells us that their hypercohomologies are the same. And then property 2 says that because this is a complex concentrated in degree 0, we just get back normal cohomology here. And so then for a variety, a complex variety, we then just get this chain of isomorphisms right here. And that tells us that this sort of satisfies at least the bare minimum properties that we sort of expect. Cool. So that gives us steps 1 and 2 in our strategy to correct this. So and now what we'd like to do is we'd like to figure out some way that we can actually compute hypercohomology. And now it turns out the easiest way to do this is to briefly step into the setting of abelian categories. Yeah, so we're going to, for the next few slides, just F is going to be some complex in an abelian category A, and we're going to develop here, we're going to develop here a machine to compute the hypercohomology of this. So the first thing we need to do is we need to systematically filter each term in this complex to obtain a filtration of the entire complex. So what I mean by that is, because this is a bounded complex, we're able to start at some index. So if we have our complex here, this is 1, then what we're going to do is we're going to just filter every term of this individually. Let's call this that. This is going to be F1, 1, etc. And we're going to filter every term and just require that, that all of these squares commute. And once we do that, that gives us a filtration of the entire complex, in that each one of these levels of the filtration is itself a complex. And we're going to call that just the filtration of our complex F. So that's great. Once we do that, we're going to associate to this filtration a graded object, which I don't know how to pronounce in words, so I'm just going to call it grade fill. And grade fill is defined like this. It's this guy, and since it's a graded object, as you might expect, it's a direct sum, and it's just a direct sum of all of its individual pieces. And these individual pieces are sort of the only thing they can be, which is just quotients of the pieces of the filtration. So this is fill I, quotient fill I plus 1. And now this does make sense, because as I've set it up, this is a decreasing filtration. So the I plus 1 term is a subset of the ith term. So this is called, this guy right here is called the associated graded object, and that's sort of all we care about right now. Great. And then if we take a step back, and if we take a functor, now this seems sort of random, but if we take a functor on abelian category, so from abelian category A to B, then this fill object gives us a filtration on this on these terms right here. So these are the ELF hyper right derived this is the ELF hyper right derived functor, which sounds entirely made up to me, but we have hyper cohomology, so we also have hyper derived functors, and it turns out the fill also gives us a filtration over in B. Yeah, so and once we have that, it seems somewhat natural. We have this object right here, and we have this object right here with two graded objects, and we can check that these both live in the category B. And so it's natural to ask, do R and grade fill commute? So that is, do we have this isomorphism between these two things? And now to answer that, we define a spectral sequence. So we call this the spectral sequence of the filtered complex. And it's defined like this. The first page is just all of these terms over on the left. And it turns out that once we check this, it degenerates to these terms on the right. And so if we can rephrase this question, because this isomorphism right here holds exactly when this spectral sequence degenerates on the first page. So this gives us a nice way to rephrase this question. Now, as you might expect, this process varies a little bit depending on the method by which we choose the filtration. The first filtration, the easiest filtration, most obvious one we might choose is something called the Hodge filtration. In fact, it's obvious enough that it's endearingly referred to apparently as the stupid filtration, if you want to look that up later. But I'm not going to write that down right here. But once we choose the Hodge filtration, and then it simplifies things quite a lot. So the first page of our spectral sequence, we get rid of these hyper right derived functors in favor of, we get back honest just right derived functors, and that's very nice. And when we're in this setting, we note it's obvious that E infinity, the infinity page, is a subquotient of just the first page. And so that means that we always have, at least for abelian categories where dimension makes sense, we have this inequality right here. This always holds. And now when we have equality, we have equality right here exactly when the E infinity page and the first page are the same. So this is another way to rephrase the question, just this degeneration of the spectral sequence, this Hodge spectral sequence now, because we've chosen the Hodge filtration. It degenerates on the first page exactly when we have this equality of dimension. Yeah, so back to our setting where we're working with varieties. In the case that X is a variety over K with some additional assumptions, the Hodge spectral sequence becomes this. Right here we have, on the first page is made up of terms that are given by sheaf cohomology, which is great. And when we take a direct sum of that, we get back Hodge cohomology. And then the E infinity page, we get back exactly de Ram cohomology. So this gives us, this finishes our third step. This connects Hodge cohomology to de Ram cohomology. And by lemma 1.2, this degenerates exactly when we have these equalities, that all of these equalities hold. And this is the same as saying that this degenerates on the first page exactly when de Ram cohomology and Hodge cohomology are isomorphic.
Could I ask a question real quick?
Yeah, sure. I can't promise I can answer it. But.
No, I think probably. So I'm sure this would be obvious if I really understood the constructions here. But because we're working over a field K, do we just know that there isn't torsion anywhere in sight, and that's why we're working with dimensions? Okay.
Yeah, no, this is actually something I don't know, and this is something I'm confused by. So this is true, say, if we were working in like K vector spaces, then this construction is the same, and then it would be fine. But I do believe that we know, because we have a variety over a field, that we don't have torsion anywhere. So equality of dimension does imply equality of objects, I think. Yeah.
Thank you.
Yeah. Great. So, and now the final question here to answer is just when does this equality of dimension hold? And this is where one might apply in characteristic 0, at least. I think Hodge's proof of this used Serre's Gaga principle, but it turns out that Serre's Gaga principle does not work with in the characteristic P setting. However, it turns out that the characteristic P setting can be cleverly manipulated to prove the characteristic 0 setting, which I think is very, very cool. I don't have time to talk about that exactly, so I made a slide this morning that just gives a very rough overview of what happens. But so if we do have this isomorphism in characteristic P, then we can move to the characteristic 0 setting by just doing this. So first, we would just take, if we have a characteristic 0 field here, then we can realize K is just an inductive limit of its sub-Z algebras of finite type. And then once we do that, apparently, I'm told that there exists one of these, once we go far enough along, that that we can find one that gives us back our scheme X in a nice way, that one of these guys, it gives us back our scheme X. So, and then once we do that, we realize, just because S right here is a quotient of Z adjoined a bunch of stuff, that since it's a Z algebra of finite type, that means we can take a quotient of some prime ideal which lives over a prime in just the integers. Once we do that, we end up with something that corresponds to X but is characteristic P. And if you do this correctly, this is the part I don't really understand. If you do this correctly, then the dimension is preserved. And so it suffices to prove, once you do this, you can prove it for this new characteristic P object, and that gives us the result for our original characteristic 0 object, which I think is kind of cool. All right, and that's all I have today. Yeah, so thank you all for bearing with me. Yeah.
Are there any questions?
I'm curious about, like, I know that Tate proved like a special case of this, where he assumed n equals 1, first of all. So like, it's really bad. But he also assumed, I think the more important assumption might be that X is a abelian variety. I'm curious about, if you interpret things this way with spectral sequences, how does the assumption that it's an abelian variety, like, is it possible to use that with this kind of technique?
I have no idea, honestly. Yeah, these assumptions in algebraic geometry are I'm still pretty confused by which assumptions we want where, honestly. So I think the source I'm working with primarily right here is I also can't pronounce it because he's French, but it's Delane Illusi, I think is how you say it. It's a
De ligne and Illusi.
Is that great? Yeah, there you go. Yeah, I think he does it. So I think he does it more generally just for schemes, nice enough schemes. And usually, I think I think he wants proper irreducible schemes often.
Yeah, I don't know the theory, but I read that Schultz also recently did it for rigid analytic varieties.
Oh, really? Huh.
I think that was the deal.
There you go. Yeah.
But the thing is, I don't really know about the spectral sequence stuff, so
Yeah, the spectral sequence stuff was the biggest
Yeah.
hurdle for me too. I'm still trying to wrap my head around all of it. Yeah.
Are there other questions? It was a nice talk. It really was.
Thanks.
We have the next talk in 3 to 5 minutes, 3 to 6 minutes.